Hello everyone. So today in this lecture we'll be covering modern physics theory, and today's lecture will be based on the particle nature of the light, that is photoelectric effect. So before going into the insights and the depths of this, let us discuss a little bit of history. Now history says that around 1600s to 1700s, it was said that there's a debate between Newton and Huygens, that Huygens said that light is a wave, whereas Newton said that light is a particle. Well, that during that time when the discussion took place, it is said that Newton had a fame, and well, I won't be partial here. So I'd say that Newton's theory was taken correct. I don't know why, but Huygens wave nature, the theory behind Huygens wave nature, was later approved by an experiment called YDAC, which is called Young Double Slit Experiment. Young Double Slit Experiment showed that Huygens wave nature actually holds true. That time Newton's particular nature was kept aside and thought that it was a wrong one. But later again, another experiment was found that we'll be discussing here, that is the photoelectric effect. Photoelectric effect again proved that the light exhibits particle nature. Now, why this was the conclusion that light must exhibit particle nature, otherwise it couldn't have shown photoelectric effect. Now, let us see about it. First of all, apparatus was set up to study it. The apparatus is a vacuum tube. Means this tube is almost evacuated. We generally use the vacuum pump here to evacuate all the air out of the tube, so that the collision between the electrons and the air particles can be negligible. We take an emitter and a collector. On the emitter plate, we incident light, and the light, what is the function of this light? The light will strike an electron on the metal surface, and it will excite the electron, and that is by giving it some kinetic energy. Now the electron will move towards the other plate due to its kinetic energy, or the energy due to the motion. Hence, it will strike the other plate, which is named as the collector. Thus, we'd expect a generation of current in this situation. But there's a catch. We connect a high voltage source such that the collector is kept at the negative potential and the emitter is kept at positive potential. We know that electrons are negatively charged, so the negative plate will try to repel the electrons and the positive plate will try to attract the electrons. That is why electron will have some net retardation opposite to its motion. Thus, if we increase the high voltage source up to a certain limit, what we will observe that the ammeter reading slowly decreases to zero. Right? I have written it in form of theory below. You can check that rate of electron emission is measured by an ammeter. We increase the high voltage source slowly. Now we increase the high voltage source slowly. We expect that the force on the electron to increase. Thus, we would expect that there will be a certain point of time that the electrons should come at rest. Then what will happen? That time the ammeter reading will turn out to be zero, and this voltage which you get on increasing the AGV source passes statically, so that the electron emission can be stopped, or the, actually better to say that the ammeter reading can be made zero, is called the stopping potential. And the relation between stopping potential and the cutoff energy is phi s is equals to E times Vs, and if you write in electron volts, then it will be only Vs. I hope you get it. Now, what is the objection with the classical model? Well, the concept is actually a little interesting. Basically, it's a experimental chapter. You cannot exactly define everything on pen paper here. So I will be giving some data. Well, what is the exception which comes regarding the classical model? So basically, it's a practical chapter. Everything is done using an apparatus rather than writing theories on pen paper. So what are the observations? The observations are that if the model followed classical theory, then maximum kinetic energy of the electron should be proportional to the intensity. The photoelectric effect is independent of frequency or wavelength of the light, and electron takes time to liberate or escape from the surface of the metal. Now, what does the first point says? First point says that kinetic energy of electron is proportional to intensity. Now, coming back to the apparatus, suppose I take I1 as the intensity and frequency as nu. Then what would happen? Suppose here the ammeter reading is not zero. In this case, the ammeter reading is not zero. But if you decrease the intensity value very less, but keeping the frequency constant, you will observe that ammeter may decrease its value, but it will not turn zero, right? So we can say that the electron will be emitted easily. Now it's also said that electron energy is proportional to intensity. Suppose I assume that the energy required means the high voltage source is kept at a potential higher than the energy of the electrons. Suppose the frequency is nu, so the energy of electrons is lesser than the E times Vs, where Vs is the cutoff voltage. Now, it is observed that as you increase the intensity of the light, you will see that there will be no reading in ammeter. It is proving that there is no dependency on the intensity of the light with the kinetic energy of the photon. So we just visualize point 1. Now point 2 says that photoelectric effect is independent of frequency of lambda of the given light. Now this statement is also wrong. It was according to classical theory. It says that classical theory says that there exists no such frequency that energy will be absorbed by an atom that will be equal to I time area, where I is the intensity and A is the area of the atom. So there is no involvement of term of frequency or wavelength. But the catch is that if you decrease the frequency beyond a certain limit, then the observed the observed reading will come out to be zero. Hence, photoelectric effects should depend on lambda and nu. Hence, we can say that this point is actually wrong. Similarly, another observation that is found during this experiment is that the electron emission takes place instantaneously. But in classical model, it says that electron takes time to liberate from the surface of the metal. Well, we'll be visualizing this through a problem. The problem says a laser beam of intensity 120 watt per meter square is incidented on a sodium surface whose threshold or cutoff voltage is 2.3 electron volt. Radius of sodium atom is zero point 0.1 nanometers. Then you have to find the time required for the photoelectric emission. So I can say that power times time is equals to energy required. The energy required would be the threshold energy. Hence, substituting these values, we'll get delta T is equals to E by IA, and which will come out to be roughly zero point 0.1 seconds. Well, zero point 0.1 second is small, but it's not that small that it cannot be measured. Right? If we observe in case of the experiment, the experimental value says that the photoelectric emission takes place in about 10 to the minus 8 to 10 to the minus 7 or 10 to the minus 9 seconds, which is extremely small. Zero point 0.1 second is still measurable, but this time is almost means it's very difficult to measure this time, right? So we can say confidently that classical theory does not work here. Classical theory basically doesn't work here. And this kind of analysis was also given in one of the previous INPHO question paper. Well, I have just taken a part of it, but I don't know whether the values are same or not, but probably the values given were different, and a part was given for analysis. Now let us see the observed concepts. First thing is that the saturated current is proportional to the intensity of the light. As you increase the intensity, the saturated current will increase, and saturated current Is is proportional to the intensity. Let me give it a small letter Is, right? Well, we'll be deriving the formula for the saturated current during the later time. For now, just see that if you keep the intensity be I1, if the intensity is I1, then the saturated current is small I1. If intensity is 2I1, saturated current is 2I1. This point is to be noted. Hope you get it. Next thing, that no photoelectric emission occurs if the value of this is called h nu, and this is the energy of one quanta. We'll be discussing about the quanta in the later stages. Is less than the stopping potential phi s. This process is instantaneous, almost 10 to the power minus 9 seconds. So these three observations prove that light must exhibit particle nature, not wave nature. Okay. Now, what is this formula? This formula looks pretty interesting. Let us investigate. Quantum theory was proposed by Max Planck, and it says that light is composed of tiny particles called quanta or quantum, whose energy is given as h times nu, where nu is the frequency of the photon or the light source, and it can be further written as hc by lambda. Lambda is the wavelength of the light. It is said that if you project a light towards a metal surface, then electron gets ejected. Then the kinetic energy of the electron is given as h nu minus phi s. Now this phi s term is pretty interesting to discuss. Phi s can be, you can say it's that this is the maximum kinetic energy possible for the electron. Why maximum? Let me explain you. Now there will be some electron. This is the energy diagram I am drawing. There will be some electron residing on this surface. Now the energy required to eject the electron just from the surface will require an energy of phi s. This is called the stopping potential. Just assume that it is like a surface tension. Like in a liquid, if you have any particle stuck to it, the energy required to remove this particle is phi s. That is the stopping potential. That is threshold energy. Pardon me. Now there will be electrons which are bound a little closer to the atoms of the metal. So in that case, it has to first cross this barrier, then again a phi s extra value has to be added. So this is the maximum kinetic energy possible for the electron, as we discussed in case of photoelectric effect. Now, if kinetic energy is found to be zero, then we say that nu is equals to phi c by h. We call it specially as nu c, which is called the cutoff frequency. Similarly, cutoff wavelength is given as hc by phi s. Hope you get it. And the value of h is given as 6.636 times 10 to the power minus 34 joule second. Similarly, the kinetic energy is h nu minus phi s. Now, what is the amount of potential that is should be applied on the high voltage source such that the electron just stops before reaching the other plate, that is the collector plate? We term it as Vs. Now, E times Vs is the energy decrement of the electron. So, E times Vs should be h nu minus phi s. Hence, if you plot a graph between Vs and nu, will or the frequency, will get Vs is equals to h by E into frequency minus phi s by E. Thus, intercept will be phi s by E and slope will be h by E. So, using the graph, we can derive the value of h. Now here's a small analysis that suppose you have a red light. You have red light and the energy of red light is given as hc by lambda. So you can further write it as 3.06 times 10 to the power minus 19 joules, which is nearly 1.91 electron volt. And the momentum of photon is given by an interesting equation, that is E is equals to Pc, where P is the momentum, E is the energy, C is the speed of light. Hope you understand till this portion. Now we are going to take the last topic, that is the saturation current. Suppose you have a plate, this is the receiver or the transmitter plate, and on this plate light of intensity I naught falls. So you would expect that this I naught strikes, each photon actually strikes one electron. In general, if quantum efficiency is assumed to be 100%, then one photon kicks out one electron. This is a very important concept you must remember. So how many photons are there? How many photons strikes per unit time? It is given as I naught A, that is the power of the source, upon h nu, where nu is the frequency. You can further modify it as I naught A by hc into lambda, where lambda is the wavelength of the light source. Get it? And if you find it current will be just charge into the number density or the number of charge carriers, which is given as Ne, and finally you will get I naught A lambda E by Hc is the saturation current. Suppose the quantum yield or the photoelectric efficiency is given as eta, and eta is not equal to 100%. If eta is not equal to 100%, then we say that saturated current is given as I naught A lambda E upon Hc into eta. So these two formulas should be memorized by an individual. Well, if you don't memorize, you must at least know how to derive this formula. So now we'll be seeing a question related to this problem, and the question is from build your understanding of Pathfinder. Well, here's the question. The question says a plate of area S is connected to a battery of EMF E through two identical resistors A and B of resistance R, is uniformly illuminated by monochromatic light of wavelength lambda. The photoelectrons emitted from the plate are collected by the earth via grid as shown in the figure. The intensity of the light that reaches the plate after passing through the grid is I naught. Resistance of the plate to flow current along its length is given as R naught. Quantum efficiency of the photoelectric emission is given as eta. You have to find the current strength through each of the resistors A and B and denote the modulus of charge on electron as E. Now here's the interesting thing, that the concept involved is, if the current through resistor B is I1 and current through resistor A is I2, then I2 is not equal to I1. This may seem a little surprising, but the theory behind it is, suppose this is my plate and the current entering from resistor B is I. Since the voltage is adjusted positive to negative like this, so we'd expect the current to flow in the anti-clockwise direction, right? So I'm assuming that here's the flow of current. Now consider a small strip of length dx and intensity of I naught to fall on it. So what is the increase in current di? We would expect it to be I naught lambda by hc eta into area into E, where area is given as W lambda I naught eta w into dx a by hc, where a is w into dx, pardon, into e. And it's also given that the resistor of this plate is given as r naught, right? Here is somewhere mentioned, yeah, it's r naught. So the voltage induced between these two points is important, which will be r times ix, where r is the differential resistance of this strip, which will further come out to be r naught in, well, keep it dr, dr naught, which will further come out to be r naught dx by l into I as a function of x. Now suppose the current through this portion is I. Now as photocurrent generates, so electron flow will be just perpendicular and outside. So we know that the conventional current flow is opposite to the direction of electron flow. So we would assume a di current to be flowing inside the plate, and thus resulting a current of I plus di. So I can say di is equals to I naught lambda eta e into w into dx by hc. So I can say I as a function of x is equals to I1 plus I naught eta lambda e w x by hc. So just putting the values here, r naught by l into dx into, what is it, I1 plus I naught eta lambda e w x by hc. So this is the differential voltage induced between these two points, where this is the positive and this is the negative. Well, I'm wrong here, it will be opposite. This is positive, this is negative. So the differential voltage is this, and integrating it along the length, you will get r naught I1 plus I naught eta lambda e s r naught by hc. Hope you are getting it. And there will be a factor of 2 if you integrate, because here's an x, so there will be a factor of 2. Hence we get the resulting value of the voltage across the two endpoints of the square plate. Now the question comes is about what will be the voltage across the resistor A and B. Now across B it will be RI1, and across A it will be RI2. Now I2 is given as I1 plus I2 is given as I1 plus I naught eta lambda e w l by hc, which is given as I1 plus I naught eta lambda e s by hc. So just summing of the voltages, you will get Ri1 plus Ri1 plus I naught eta lambda es by hc into R, plus the voltage across the plates, which will come out to be R naught I1 plus I naught eta lambda es R naught by 2hc. Further evaluating, you will get I1 into 2R plus R naught plus I naught eta lambda e s by hc 2hc 2R plus R naught is equals to V. Hence we get I1 is equals to V by 2R plus R naught minus I naught eta lambda e s by 2hc, and hence we get our final result. So this will be the current through the resistor B, and the current through resistor A is equal to I1 plus, will be I2 is equals to V naught by 2R plus R naught plus I naught eta lambda E s by 2hc. So that's the solution. And if you want to practice more from Pathfinder, you can try other problems like builder understanding. Question number 1 is also moderate to easy, it's a decent level. Question number 3 is related to thermodynamics, it's also from builder understanding. you can try question number 6. So question number 6 is also a nice problem. This involves just a bit of concept. This paragraph question also you can try. Just you need to know some basic concepts of EM waves, and also it's mentioned. And the intensity of EM waves you can use here is 1 by 2 epsilon naught E naught square into C. Yeah, one more concept to discuss here about the EM waves, that you may be given some questions where you will be given some complicated trigonometric functions of the light. Suppose E naught 1 plus cos omega t into cos omega t. In this kind of questions, it is basically the superposition of the electric fields of two different waves of different frequency. In these kind of problems, just separate the two waves. You will get E naught cos omega t plus E naught 1 plus cos 2 omega t by 2. Basically, we will get two EM waves, and we have to just evaluate these two. We will get frequency equals to omega by 2 pi, and other frequency as 2 omega by 2 pi. Accordingly, we'll be substituting the values and finding the stopping potential and all the other relevant terms. So, hope you enjoyed it. Thank you. Have a nice day.